Hello everyone, welcome back. In this lecture we're going to be discussing about multiplexers and logic gates. You guys might have already learned about basic logic gates and multiplexers. The idea of this lecture is to introduce you or say going over the mechanisms how we can make use of multiplexers for designing logic gates, or in other words, multiplexers are considered as universal logic, that you can create any logic gate using a multiplexer. All right. This is kind of important to know because you see there are Mux-based FPGAs which have all 2:1 or 4:1 or different multiplexers, and using those multiplexers only different logic gates are being created, or logic is being routed in those FPGAs. Or in general, you can if you don't have AND gate IC, you can use multiplexer ICs to create an AND gate on AND gate. So let's talk about two input multiplexer. So what it is? So as we know that we have two inputs, X input, one input, and Y another input. Okay. Now what multiplexer does, it passes on to output either of the inputs I1 or I2. Okay. Now which input will be passed on to the output Z depends on the select line. Okay. So this is the select line. Okay. So if select is 0, then output Z will have the signal routed which is coming on to I1 pin or the value X. And when the select input is 1, what the output will have? Output will have the signal routed which is on the I2 pin or the second input to the multiplexer, or the second value which is input to the multiplexer is Y. So this is a simple basic fundamental about it, 2:1 multiplexer. Okay, selecting one out of two inputs. Great. We can say think of excitation table if we want to write for this multiplexer, is simply that when we have S is the select input is 0 or 1. So when S is 0, whatever is coming on the X line or the X value or input 1 will go to the output. In the same way, when S is 1, whatever is on the Y line or the Y value or the second input will go on to the output. All right, and we can represent its characteristic equation. Okay, the output would be X dot S bar plus Y dot S. Okay, very simple. Now, how we can use this 2:1 multiplexer to create different logic gates? That's we're going to be learning about. Good. So now let's see the very first basic gate, NOT gate, okay, or an inverter. So what an inverter is, that basically whatever is on X input, output will be the inverted of that value. Okay, so if X is 0, output will be 1, X is 1, output will be 0. So this is a truth table for inverter. Okay, and you can write a Boolean equation, characteristic equation for inverter, Z equal to X bar. Now interestingly, if we want to design, or if we want to use this 2:1 multiplexer to design this NOT gate, okay, what we can do in a very simplistic intuitive form, we need to first remember that we need to make use of this select input somehow, no matter what logic gate we are designing. Okay, always remember we got to make use of select line somehow. Good. Now here, if we look at the equation number 2 and equation number 1, so what the characteristic equation of inverter is Z equal to X bar. And if we see the equation of 2:1 multiplexer, it says X dot S bar plus Y dot S. Good. Now, if intuitively we think of, if we replace, say, S, okay, with X, we already have, say, X bar here. Good. And this input X, if we connect it to 1, so we got 1 dot X bar, which is basically Z equal to X bar. And if somehow this whole term we can make it to 0, then we are good to go. Now, as we already said, if we say X is S, then Y basically it got to be 0. Okay, then 0 multiplied by whatever it is here doesn't matter, because 0 logic 0 multiplied by anything becomes logic 0. So we can, intuitively got an idea that what should be the characteristic equation in terms of making use of multiplexer inputs and select line. Okay, so let's see. We can write it, in other words, by equation number 3, that simplistic form, that one input X is 1, and select line, if we route the X input to select line, we can achieve the desired property, which is G equal to X bar, and the second input is 0. Or in other words, we can connect the 0 input line, okay, or line number 1, input 1, to VDD, and another input to VSS, okay, for the multiplexer. And very simple, that when X select, which now the X input you are giving to the select line, so whenever S is 0, it will route the input 0 input, or this is, let's say, I1, consistent terminology what we were using throughout in this lecture. So when this is S, okay, so when S is 0, it will route VDD to the output, or simply, you got desired property that when input is 0, output is 1. All right, and when other way around, when your select line is 1, output is routed to VSS, which is logic 0. All right. Very simple. So always remember, we got to make use of the select line somehow while thinking in terms of multiplexer and gates. Okay, let's talk about AND gate. So what essentially is the AND gate? You guys might be knowing or learned about this gate. Nevertheless, what it is, basically the function of the AND gate is very simple. When both the inputs are same, or both the inputs are, I shouldn't say same, I should say 1, then only the output will become 1, okay, or logic high, okay, logic 1 high. Otherwise, it stays at 0. We can say the characteristic equation X dot Y. Now, if we see the equation 4 and try to come up with this equation 4 from the multiplexer's equation, what we notice here, we need G equal to X dot Y, and in the multiplexer's equation, if we notice here, we have Y already here, and if we replace, select S with X, then we can achieve our desired function, which is X dot Y. Okay. However, what do we do with this first term? Well, we need to make it 0 somehow. Okay. So as we already said, it is x. So what do we do with this x? X is nothing but the one input to the multiplexer. Well, it's simply you can connect it to logic 0 and you achieve the desired function. Okay. Or in other words, you can simply write this by equation number 5. You have connected the select input, okay, a multiplexer with the input x, and whatever was coming on the line x, okay, or 0 line or first input, you have connected to the VSS or ground or logic 0. All right, and then another input is unchanged and you achieve the desired function of the AND gate. Very simple. Now let's talk about OR gate. Similar to AND gate, OR gate has a opposite function. What it is? Well, it says that the output is 0 only when both inputs are 0. Otherwise, output stays at high or logic 1. Good. Equation, we can simply write x plus y, Boolean equation. Okay. Now, think about, we need to come up with this equation, g equal to x plus y, and we have z equal to x dot s bar plus y dot s, the multiplexer's equation. So intuitively, what we are trying to say, we are just trying to come up with this equation in the form of multiplexer's equation, and we need to make use of select line somehow. Okay. So think about, if we give s as y, okay, then we achieve this function s as y. Okay. Now here we set s as y, and now if we multiply this y with 1, okay, it stays y. So what we did here, we, whatever was coming on y line, we connected it to the high. Okay, and now x, okay, x is here. So in this equation, when we say select input is y, okay, so now if y is 0, for example, then y bar will become 1, and 1 dot x is actually x. Okay, so it's a bit tricky, but a very simple intuitive idea behind it. Or in other words, you can say that, okay, I'm gonna connect the select line with the y input line, okay, and whatever was coming on y, I'm gonna connect it to the high value. Okay, very simple. So got the idea about OR gate. Now we learned about inverter, that is NOT gate, AND gate, and OR gate. Now these are 3 basic gates. Now making use of 3 basic gates functions, we can create more complex gates. AND gate. Now you might be familiar with the basic function of NAND gate, but nevertheless, let's talk about it. It's a combination of AND gate and an inverter. Okay, and if we see its truth table, so what we find is that the function of the NAND gate, well, when both the inputs are logic high, then the output will be at logic 0 or low logic level. Okay, and if either of the input is 0, or inputs are not matching, either 0 0 or 0 1, output stays at logic high. Now we can write a characteristic equation in the form of equation 8 for this NAND gate. Okay, so if we try to solve this equation, we can also write this Boolean equation in another form, x bar plus y bar, and bingo, what it is nothing but the OR operation. Okay, OR operation of 2 negations, or whatever is coming on input 1 and whatever is coming on input 2. If we negate those things and add those, do a OR operation, then we can achieve the desired function. So that's it, simple trick. Okay, so as simple as that, like we learned for the OR gate, for X and Y input, simply the OR gate function for X bar and Y bar input. Okay, simple. Now we can make use of this little simple trick to come up with the equation for in the form of multiplexer for this NAND logic gate. Okay, so we connect the S select input with X, and whatever is coming on Y, we invert it. Okay, that's the trick. That's about it. And the X line connects to the high. Okay, and the X line connects to the high, and select is connected to the X or the input, one of the input. Good. So this is a simple representation how we can make use of multiplexer to come up with an AND gate. All right. Now let's we can further draw this circuit that we got rid of our NOT gate. We put equivalent 2:1 multiplexer. Okay, the output of that inverter goes to 1. That is second input of the multiplexer, and X on the select line, another input. Okay. Now let's talk about NOR gate. As we discussed about NAND gate, in a similar way NOR gate functions, but in the other way around. What NOR gate does that when either of the input is 0 or 1, then it always gives you 0 because of this inverter sitting at the end. Okay, and when both inputs are logic 0, then only it will give you logic high. The characteristic equation is simply, and we can solve that equation further using Boolean algebra principles, and we can come up with X bar dot Y bar, and bingo, what it is nothing but the AND gate operation. And we learned about the AND gate just on the previous slide. But here the AND gate is simply ANDing the X bar and Y bar, and we just need to use that simple principle, okay, to come up with the equation in terms of multiplexer inputs for this NOR gate. All right, how we can come up? Well, it was a very simple thing that see, we have S bar already. So if we replace this S, okay, or the select line with the second input Y, okay, and the second input line we connect it to 0, okay, and first input line we connect it to the inverter or inverted logic of the first input line because of you know, this equation as we came up with in the equation 10, and then we reduce down to X bar dot Y bar, we achieve the desired function. Or we can represent it in a diagram in this way. Okay, so X input, first input, okay, connected to 0 line of the multiplexer is inverted, and second input, okay, is connected to the logic 0, ground, VSS, and the select line is connected to the second input, which is Y. Okay, we can also simplify further. Now let's talk about XOR gate. Another very simple concept or simple gate. The function of XOR gate is simple. When both inputs are different, then only is going to produce 1. Remember, when both inputs are same, whether it is 0, 0 or 0, 1, XOR gate gonna give you 0. we can write its characteristic equation, xy bar plus yx bar using equation 12. And again, now we have to find or design this XOR gate using 2:1 multiplexer. So we have here the multiplexer's equation, here the XOR gate's equation. Now try to find the similarity here. Okay. So we already have this multiplexer's equation, and we are trying to find the answer. So simply, if we say we connect the select input line with the Y, okay, and Y with the inverted logic, whichever is on X, then we achieve this desired function. Or in other words, whatever is here on 0 line or first input, we give its inverted value to first line or the second input of the multiplexer, okay, and we call it, say, first input X, and the second input Y, we connect it to the select line, okay, and we achieve the desired functionality of the XOR gate. We can further simplify it. We just got rid of that inverter here and replaced the multiplexer circuit. Very simple. Now if we want to say we have one more gate left, which is XNOR, and what is the functionality of the XNOR? Is the opposite way of the XOR, that when both inputs are different, then we're going to get logic 0 at the output. And when both inputs are same, whether it is 0, 0 or 1, 1, we're going to get 1 logic high at the output. Its characteristic equation, we can represent it by equation 14, which is x bar y bar plus xy. Again, the same principle, similar fundamental, that we got to make use of select line or select input of the multiplexer somehow. Okay. So these two equations, 1 and 14, and how we can convert this equation number 1 in the form of 14. Good. That's our job. So very simple, that if we say, okay, if we connect our select line with the Y input, okay, and Y line with the X input, okay, and X line inverted X, then we achieve the direct desired functionality. Or in other words, we can represent via this circuit that X input is inverted and feed it to the 0 line of the multiplexer, and on the 1 line, that is second line, direct X, and Y input is going to the select line. Very simple. We can further simplify it. Got rid of that inverter, replaced it with the inverter circuit in the form of multiplexer. So good. It was a fairly simple principle, intuitive ideas we have used to come up with the gate circuits using 2:1 multiplexer. Hope you guys have enjoyed this lecture. Thank you everyone for subscribing and liking lectures on YouTube. If you are facing difficulty or need private lessons, feel free to contact us. And once again, those who have not subscribed, please do subscribe, like, and Google+. We appreciate your feedback and support. Thank you.